Today, we sort of have a recap of some basic electromagnetism that most of you should already be familiar with from some previous courses, right? And look at this important concept of total internal reflection, which is important for optical waveguides and optical fibers, right? So we start by deriving the electromagnetic wave equation, as we discussed last time in sort of source-free dielectric media, right? And so we start with the Maxwell's equations. So the source-free Maxwell's equations. Right, so let's start with this curl equation, and we take another curl on both sides. Okay. And so we also consider non-magnetic, the medium to be non-magnetic, which means basically the permittivity is just free space permittivity, right? So basically this d mu we can just write as mu naught h, right? So on this right hand side we get that, and now we can use the second Maxwell curl equation, right? So del cross h, we know this is equal to the derivative of the displacement vector in time, right? So on the left hand side here, if you use this identity, vector identity here, you get that, right? So del square is basically del dot del, right? Second derivative with respect to the spatial coordinates. And then on the right hand side, so again, so if you have d here, we can write that, let's say, as epsilon times e. So we are considering isotropic media, right? Which means the d vector is parallel to the e vector. Right. So this epsilon naught is, of course, in general not equal to epsilon naught, which is the free space permittivity, but there will be some dielectric constant. Okay, so now on the left hand side we have two terms. So if we consider this del dot e term, right? So we know that so another Maxwell's equation is that the divergence of d is 0 in a source-free medium, right? So if you use this expression for E, so in general, let's say E, or sorry, epsilon, as we discussed last time, so if it's a homogeneous medium, then epsilon is a constant, right? So in that case, so if you have a homogeneous medium, which means every point in the medium is the same, right? Then we can just take this epsilon out common, and then we get this, right? So that means del dot E is identically 0. Right, so which means that this term will vanish. So if you have a non-homogeneous medium, right, which means, so if you have a non-homogeneous medium, so this dielectric constant would actually be a function of position. So each point is not exactly the same, right? So then, of course, we can't take this outside the divergence here, right? So in that case, this would become okay. So this is for non-homogeneous. So from here we get that del dot E is that. Okay, so it depends on the gradient of this dielectric constant, right? So normalized to the value of the dielectric constant, right? And then dot product will be. So in general, for non-homogeneous medium, this is not zero, right? For homogeneous medium, this is zero. Gradient of epsilon is zero because epsilon is a constant. For non-homogeneous, it's not zero, but for most practical cases, turns out that this is actually very small. Okay. So basically, this term sort of the magnitude of it tells you how much. So, what is the percentage change in the dielectric constant over a scale of 1 wavelength? Okay, that's sort of the magnitude of this quantity. And typically, even if you have a medium where the dielectric constant is changing, right, it won't change so rapidly that over 1 wavelength you get a huge change. Okay? So that's why this quantity typically will be very small that we can actually neglect it compared to the other term. Okay, so we can sort of neglect this term. But in some special cases where like the dielectric constant is actually changing in non-negligible manner, you cannot neglect this term. Okay, but for our purposes, for most waveguides, optical fibers, this approximation is very good. Okay, so basically in a nutshell, you can neglect this term. Right, so we end up with the familiar looking wave equation that you must have seen before, right? So this is also known as the homogeneous wave equation because this is exactly valid for homogeneous medium, right? It's we will also sometimes use it in the course for a non-homogeneous medium, but making this approximation, so not exactly valid, but for homogeneous medium is exactly valid, so that's why it's called a homogeneous wave equation. Okay, so this is sometimes written in a different form that you might have also seen. So we know that, that this dielectric constant is related to the refractive index of the medium, right? So the speed of light in the medium. So if you look at this quantity V naught epsilon, that's that, right? And mu naught epsilon naught we know is 1 over c square, right? So, and then the refractive index of the medium is defined as the square root of this dielectric constant, right? So this is the refractive index of the medium. So again, mostly we will consider lossless media, right? Which means there is no absorption of light in the medium, which means this epsilon r dielectric constant is a real number and also the refractive index is a real number. Right? If you have absorbing media, then these become complex numbers. Okay, so then basically I can write this as n square by c square. right? So then the wave equation I can write as that, right? So this directly tells you now that this is a wave which is moving at the speed of c over n. Okay, so and depending on the medium, we can have different kind of solutions, right? So in the course, we'll look at for a structured medium where sort of we have different diffractive indexes in different regions of space. How do we solve this equation and get so-called eigenmodes propagating through the medium, right? So simplest solutions, you know, in, for example, free space or a homogeneous medium which has the same diffractive index extending everywhere are plane wave solutions, right? So you can write the electric field as having some polarization vector, some amplitude, and then the phase goes as so there's a temporal phase, right? So omega t is the temporal phase, and then k dot r is the spatial phase. Right, you can check easily just plugging this into the equation that it solves. Question? So this plus and minus also you should know that, right? So plus means that the wave is propagating in the minus k direction, and if you have a minus sign here, so the temporal and spatial phase, if they have opposite signs, then that means the wave is traveling in the plus k direction. Right. So this is the amplitude. So in general, this is a complex number, right? So we are using the complex notation. So of course, physically, the electric field has to be a real quantity, right? So if you want to know what is the physical actual electric field, you just take the real part of this, right? But we use this complex notation because all the mathematics becomes very easy. Right? Instead of using sine and cosine, we can just use these exponential, complex exponentials, which are also known as phasors. Right? The math is easy. So we use this complex notation. So in general, this is a complex number, right? So it could have a magnitude mod of E naught, and it could also have a phase, right? Which will add on to this phase. And then this is the polarization or the sort of the direction in which the electric field is pointing, right? Because it's a vector quantity. So this is a unit vector. And again, you know there are different types of polarizations possible. So for example, you have linear polarization, which means the electric field is pointing in one particular Cartesian coordinate, right? So for example, this could be x or y or z or some linear combination of any of these, like for example, you could have like that. As long as these two are real numbers, then this is a linear polarization. Right? You could have, for example, circular polarization, where you have 90-degree phase difference between the two Cartesian coordinates. So, for example, this looks like, if you want to normalize to the unit vector, this will be something like x plus or minus depending on right or left circular polarization, right? And this I is basically the e to the I pi by 2. So a pi by 2 phase difference between the x and the magnitudes in the x and y are the same. So if the magnitudes in the x and y are not the same, then in general you will have what is known as elliptical right? So that will look like something like, let's say, A x cap plus some I B y cap, right? So now A and B are not equal, right? So linear means like the electric field is pointing towards some particular direction and it just oscillates back and forth in that direction, right? So with time. Circular means it actually traces out a circle, right? In time. And elliptical means it traces out an ellipse in time. Okay, so why are these known as plane waves? It's because the wave fronts, or like if you look at the locus of points which have the same phase, right? Those are planes. So that's why it's called plane wave, right? For example, you could have a spherical wave. So if you have just a point source which is radiating, right? Then what it gives out what is known as circular or spherical waves, right? Which means the constant phase surfaces are spheres. Right? In this case, you can check. So what is the constant phase surface? Would be then this the points are for which this is the constant. Right? So you can check. So those will be planes which are perpendicular to the k vector. Okay, so all points on this plane which is perpendicular to the k vector will have the same phase, right? And this phase repeats after a distance lambda, right, in the propagation direction. So that's the wavelength. So k is related to lambda by, right? So the magnitude of k is 2 pi over lambda, or lambda is 2 pi over k. And there's also a relationship between this omega and k, right? So again, if you just plug this into the equation, you will see that. So basically, the spatial derivative term will give me k because that's the only term dependent on space, right? So when I take a derivative, I'll get k out front, and I have two derivatives, so I'll get k dot k or k square here. Similarly, for the temporal derivatives, I'll get omega, so omega square, right? And with the omega, I have this n over c square already. So from that, basically the relationship between k and n, you can see, so you get k square is right. So that's the relationship between k and omega. Also from so again, so we are considering a homogeneous wave equation. So in a homogeneous medium, we just saw that del dot E will be 0. Right. So if you just take del dot E here, right? So you'll see that. So again, when you take the spatial derivative here, you just get k out front. So basically you get k, and then the electric field is basically the direction is given by the p. Right. So k dot p is 0. This means a transverse wave, which means that the polarization is perpendicular to the propagation direction. Right, so the electric fields are pointing again in this plane somewhere. So again, they could be any of these, but they're pointing in this plane. Okay, so we define this quantity lambda, right, which is related to k like this. So that's the wavelength. we also define a frequency like that. Okay, so this is the angular frequency, this is the absolute frequency. So this is in hertz, this is in radians. And then from here you can check basically the familiar relationship that right. So with an N. So if this is the free space wavelength, right, then you have an N here. So wavelength in the medium is lambda over N, right, where lambda is the free space. So okay, so basically K is like a spatial frequency, right? Whereas omega is like a temporal frequency, right? It's also not clear from here.
Sir, how will we know that the wave is in the clockwise direction or anti-clockwise direction when it is traveling towards an observer?
Again, so it depends on the sign here, right? So I mean, I'll leave that as an exercise to you. So plus and minus denote like the right and left circular, right? So which one is which? You can try to substitute this here, right? And then take the real part, so we'll get. So for example, with x you'll get cosine, and with y you'll get sine, right? And which one is leading which will depend on, or like which is cos and which is sine, right? Will depend on which is plus and which is minus. So you can see, you can figure out if it's rotating clockwise or anti-clockwise.
Okay.
Right. So that's the wave defined in terms of the electric field, right? So if you want to get the magnetic field, then we can use again the Maxwell's equation. So like for example, we use this equation, right? So we take the curl of this to get the magnetic field, right? So again, the magnetic field, the phase will have the same form. Okay. So the time derivative will give me like an I omega out front, right? So this will be like that, and then here again the spatial derivative just takes the k out front. Right, so basically from here I get the magnetic field is the cross product of the propagation or the wave vector times the electric field. Right, so again the magnetic field is perpendicular to both the propagation direction and the electric field, and from here we already know that the electric field is perpendicular to the propagation direction. So this is known as a transverse electromagnetic field, right? Which means both the electric field and magnetic field is perpendicular or transverse to the propagation direction. Right? So you know this familiar feature of so the K here, we have E there and E here. Many times, like we are really interested in the. So again, the k over omega here, the magnitude of that. From here you can see, right? So k over omega, the magnitude is n over c, right? Which means so the magnitude of the magnetic field is n over c times the magnitude of the electric field. Okay, so because c is a large number, typically the magnetic field value is very small compared to the electric field. right? So we are interested in this quantity H again, which for non-magnetic medium is B over mu naught, right? So from here you get that this is so again I write C over N as mu naught square root of mu naught epsilon. Okay, so you get that. So this quantity, the square root of mu over epsilon, that's known as the impedance of the medium. Okay, denoted by eta, so this is known as characteristic impedance. So it has units of ohms. That's why it's known as impedance. Okay, so if you look at free space, so this is about 377 ohms for free space. Okay, and if you have any other medium with a finite dielectric constant, this value will be smaller, right? Because you'll have another epsilon naught r. Okay, so basically the magnitude of this H is the magnitude of E divided by the impedance. So, in analogy to like an electrical circuit or something, this is like the voltage, this would be the current, and this would be the resistance. Okay, so that hopefully gives you a nice refresher to plane waves, which probably you're already familiar with. So plane waves are not really physical, right? In the sense that they extend out to infinity, right? So they have actually infinite energy, right? Because they extend out to infinity, so they are not actually physical, right? Any physical wave has a finite extent. So in general, we can write a wave, right? So an arbitrary wave we can write as a collection or superposition of plane waves. Just like any signal in the time domain, right? If you've done any basic signals course somewhere. So you have any signal in the time domain, right? Some arbitrarily time varying signal, right? Let's say some x of t. What you can do is actually write it in terms of, let's say, a Fourier series or Fourier transform. Right? You can write it as a collection of sum of different sine waves at different frequencies and different each weighted appropriately, right? So each of these are infinite extent, right? Sine waves going out to infinity. So any physical signal which, let's say, has a finite extent, you can write it as a sum of these non-physical infinitely extending waves. Similar concept here, right? So here in the spatial domain, right? Any physical wave will have a finite spatial extent. You can write it as a sum of plane waves, each of which are sort of having infinite extent, right? So any arbitrary electric field function of position and time so I take different plane waves and then weight them. So A of k would be the weight or the amplitude of the plane wave at with wave vector k, right? So Omega is also a function of k, we just saw, right? Omega is related to k. So, I mean, let's say for simplicity, we are looking at the waves propagating in the z direction, so we just take k as k z cap, right? So, basically, what we are doing here is varying k, right? So, for each different k, we have a different plane wave, and we just weight them with different amplitudes and integrate. So, add all of them up together to get an amplitude, right? So, same analysis here. Right, so this omega of k is basically k times c over n, right? And in general, for any material, actually this n is also a function of frequency. Okay, so it's not very straightforward, right? So this is known as dispersion, that the refractive index of a medium depends on frequency, right? Right, so if I look at some time t equal to 0, then you can see directly that it's just sort of adding up plane waves together, like that, right? So you can see that now these are just Fourier transform pairs, right? AK and EZ are Fourier transform pairs. So this is spatial Fourier transform. Sorry. Yeah. So, for example, like this, the electric field as a function of space. So for any physical wave, it will have a finite extent, so it sort of looks like that. Let's say, okay, so this is like a wave packet. Okay, and this packet moves. So as these different plane waves acquire phases, so as you evolve time, the different plane waves acquire different phases, right? And they all add up together differently, so this whole thing sort of moves, right? So if there is no dispersion, if this n is a constant, then this whole packet just moves forward without any distortion. But if there is dispersion here, then the different plane waves are acquiring phases at different rates. So this envelope also gets distorted, like broadens. Okay. Right. So if you look at AK, so for such a wave packet, if you plot AK, so it's centered at some k naught, and it will have some distribution of k's. Right. So k naught will be sort of the fundamental spatial frequency. Basically, like this oscillation here. Right, and this envelope, so we know that each of the plane waves moves at the velocity c over n, right? So now you add all of them up, and the speed at which this envelope moves, that is given by the group velocity, right? So that you know is given by the group velocity, so the derivative of the frequency with respect to k. So that will be evaluated at the center frequency. Right, so sometimes you also define a group index. So in analogy, so the phase velocity is c over n, where n is the refractive index or the phase index. Similarly, the group velocity we can define as c over some number, where that number is defined as the group index. Okay, and again you can take this relationship between omega and k and try to evaluate this d omega over dk and write it as c over ng, and then you can find a relationship between Ng and N. Okay, so that looks like this.
Sir, what is K naught here?
K naught is some central frequency, right, about which you have a spread of frequency. So could be anything.
Sir, it is following a Gaussian distribution.
Yeah, so it could be anything, but so typically, like if you have a Gaussian wave packet here, then this will also be Gaussian. Because so you have basically this AK and EZ are Fourier transform pairs.
Okay.
Right? So if this is a Gaussian, then this is also Gaussian, because Gaussian has this property that the Fourier transform for Gaussian is a Gaussian. But if you have some other, like let's say for example, if you have a rectangular wave packet or something here, then this won't be Gaussian, right? This will be the Fourier transform of this rectangular packet, which will be something like at same curve. Right, so fundamentally it's just that they're Fourier transform pairs. But in most practical real world cases, yeah, we approximate them by Gaussians. But they could be anything.
Okay, sir.
Alright, so that's the concept of group velocity and group index. And then the final sort of fundamental quantity I want to discuss is the Poynting vector or the energy flow. Right? So you also know that electromagnetic waves carry energy, right? The propagation direction, energy is flowing, and how do we quantify that energy is the Poynting vector. Right, so this quantity is defined as S and given by just the cross product of the electric field and this magnetic intensity.
Hello,
so it has
sir.
units of watt per meter square. Yes?
Sir, your screen is not visible.
Screen
Yes.
is not.
Screen is not visible.
Sir,
Sir, I
The
think
whole-
the
whole
video
video
just
window
blacked
है?
out, sir. The video blacked out, sir.
rejoin करो हो जाएगा.
Is it back?
Now
Is it back?
Actually, if you refreshing the page, it is coming back.
Okay. Yeah, I don't know why this happens because from my side, like it's still fine and it shows the video, but sometimes, yeah. Anyway, whenever it happens, just shout out. I'll refresh from it. Yeah, so this Poynting vector has units of what? Basically intensity. Power per unit area. So basically, the strengths of the electric and magnetic fields are telling you how much energy or power is being carried by the wave. So again, if you look at a plane wave, right, or more specifically a monochromatic wave, right, so which has a single frequency, just one omega here. So again, so S is actually a time varying quantity, right? Because E and H are time varying quantities, right? More specifically, sinusoidal quantity. But the time variation here, you can see it's a product of E and H, right? So each of this is varying at the optical frequency omega, right? Which we saw is like 10 to the 15 hertz or something. So whenever we measure power, right? So for example, we use some detector and incident the electromagnetic wave onto the detector, and it gives out like an electric current proportional to the power. But any detector only measures the average power, right? Because it can't actually respond at time scales at which the electromagnetic wave is oscillating, right? So that 10 to the 15 hertz means like you need to have a detector which responds less than a femtosecond, right? Such detectors just don't exist. So every time we are measuring average power, right? So average over time. So usually when we talk about the power carried by a wave, that's a time average. Okay, and then so you can imagine. So again, physically, these vary as some cosine omega t, right? So if you take cosine omega t and cosine omega t, you get a cosine square omega t, right? And then you take time average of that. So if you take a time average of cosine square omega t over one period or any multiple periods, you will see it's half. Right? So we get a half here. And then the real part of, if we use the complex notation, if we take E cross the conjugate of H, okay, and then take the real part. So this is a real number, and then we take the half for time average. Okay, so it's probably also familiar to you from before. Right. So for example, if you take a plane wave, right, we call, so for example, I can write electric field like that. And then I can write the magnetic field. Right, so magnitude is divided by this impedance, and then the direction is the propagation direction cross product with the electric field direction. Right, so if I plug in these values for E and H for a plane wave into here, right? So you see, you get this, right? So the power flow is in the propagation direction, and the magnitude is proportional to mod square of the electric field.
Sir, if we consider the wave in exponential form only, then the half term will be omitted.
No, so here these are exponential only.
But sir, as you said, we have taken cosine terms of them. Real part, sir, we have taken in the
Yeah, I mean, so that's why we are taking the real part here,
okay.
right? If you already took E and H as cosine terms, then you don't need to do this, right?
Okay.
Yeah, so here E and H are the complex figures.
Sir, first we have to take the real part, or after we have done the cross product, then we'll have to take the real part?
After. So first take
After,
the
right?
conjugate of
Because
H,
you
take off product, and then take it.
because you said if we are taking cosine terms of that, uh, then the sine terms will not come into action, right? Okay, sir, got it, got it.
Yeah, I mean, it's a real part of the whole cross product.
Mhm.
Right, and we can also measure so this is like the total power carried in the direction of propagation. Sometimes you are interested in the power carried along a particular direction, right? So let's say you want to know in some particular direction, right? So then we just take the dot product with respect to right? Right? Right, so in any direction, if you want to see the power flow, we just take the dot product of this S in that direction. So as you know, this is an intensity, right? Power per unit area. So if you want to know, so for example, when we have a waveguide or something, right? So it has a finite cross section, and we want to see how much power is flowing through the waveguide or right through that cross section. Then what we can do is just integrate this Poynting vector, which has units of intensity, right, over the area to get the power, right? So,
Sir, here we have not considered the phase difference between E and H.
phase difference between E and H.
Sir, there may be a phase difference of theta or anything between E and H. So that term will be also come in the S average value as cos theta.
No. So once you define E, right, then like H automatically from the Maxwell equation is defined like this, right? Now you can't like take an extra phase here. That doesn't work, right? Because remember they have to satisfy the Maxwell equation. So for example, del cross E has to be minus del V by del D, right? So basically these exponential terms have to be the same. You can't have. You understand? So.
Conducting medium, then maybe there was a difference of 45 degree between E and H.
Yeah, so then what you're saying is this becomes a complex number, right? So this
Yes,
is
sir.
impedance for absorbing or conducting medium, because here, so remember this depended on the dielectric.
Yes, sir.
So if that's a complex number, then this becomes a complex number. So that will intervene.
Okay.
But for dielectric medium, there won't be any case. Right, so power flow, again, so let's say if I'm looking at the power flowing in that direction, then I just integrate this Poynting vector in the z direction, right? So let's say depend on the transverse coordinates and then integrate over the cross sectional area. So if you're looking at the z direction, then I'll integrate over the cross sectional area dxd1. Right, so that will multiply by meter square and then I'll get you some watts. Right, and another way to say that this is a power flow is you also know that like if you have an electromagnetic field as an energy density, right? So I can define in the region of space if there is some electric field, I can define an energy density like that. Right, so I have a electric field with amplitude E and for medium with permittivity epsilon, you know that there is an energy density in the medium. Right, so energy density means this has units of joules per meter cube. Right, so if I compare with this, you can see that S is basically this velocity of the wave in the medium times the energy density. right? So again, I write this eta in terms of mu and epsilon and write that in terms of the refractive index. So from here also you can see basically what this point is showing is how the energy density related to this electromagnetic field is moving with steady C over M. So
Sir, here N is characteristic impedance in the.
no, this is refractive index, right? Because this has to be a speed. So you
Okay.
check the units, right? So this has to be what meter square. This is unit per meter cube. This has to be meters per second.
Sir, here
Okay,
you
sir.
consider just the electric field and energy density. It's not complete electromagnetic.
Can you speak up a little loudly? I can't.
Here you just took the electric field energy density because I have one more term 1 by 2 not mod A square.
Sorry, your voice is very faint. I can't.
So in the expression
you-
for energy, in the energy density,
Yeah.
you just took electric field energy density.
Yeah. So that's a good point, right? So ideally you have to add the electric and magnetic fields, right? But again, so I skipped sort of those steps. Is that so for a static electric field, you know that like I can directly write this expression, right? Again for a
Video is
for a,
off.
sorry.
Your video is off again.
Okay. Is it back?
Yes, sir.
Yeah. So so you're right? So basically, I need to add. So if I have both electric and magnetic fields in a region, I need to basically sort of add the electric field energy density and the magnetic field energy density, right? But so what's been done here is that so for electromagnetic wave, both of these are time varying quantities, right? Varying like e to the omega t or cosine omega t, sine omega t, right? So basically, again, what we do is so this is sort of a time average, right? Because so the energy density is also oscillating at 10 to 15 hertz, but when we measure energy, we are measuring a time average. Okay, so this is also actually a time average. So when you take time average, you get a half for each of these terms. Again, same principle that you get here. When you have a product of two cosine terms, you take the average, you get a half. Similarly, because you have an e square here, you get a cosine square, you take the average, you get a half. Similarly, here also again you'll get a cosine square, you take average, you get half. And then for a plane wave with these relations, turns out these two terms will be actually equal. You can check. Okay, so basically what we'll do is half of this plus half of this, which is the same as this, so you end up with this. So this includes the magnetic contribution. Is that clear? Clear or not?
It's fine, sir. And one more thing, sir, in the relation Ng equal to n plus omega dn by d omega. Actually, the way how k and omega are related, it's like a Taylor series. I have higher order dispersive terms also. So whatever you had written there, it's an approximation because I'll have higher order derivative terms.
Higher order.
Like I'll have the way how k and omega are related for a dispersive material, it will be like a Taylor series.
No, that's okay. You can write n of omega as a Taylor series, but I mean here what you're doing is just so express omega as a function of k and then take the derivative, right? So here I just have one derivative, d omega or dk. So that's why I only get one derivative.
Yes, yes. It's fine, sir.
Right, so you're right that the n as a function, so this is a function of omega, so this n of omega is a complicated function, right? It's not a linear function or anything. So, for example, if you do a polynomial expansion, you will get multiple terms. But this relation is exact. There is no other terms, right? You have only one derivative because this dg is only the first derivative, so you have only one derivative. I mean, just check, like, start from here and then.
Okay, sir.
And sir, you said that this expression for energy density, it is average. So is the average formula half epsilon E naught square or 1/4 epsilon E naught square?
So it's 1/4 for the electric field, right? And then 1/4 for the magnetic field. So from here. So when you take time average of this, you get 1/4. When you take time average of this, you get 1/4 what B naught square. But from this relation, for the relation between the magnitude of E and H or E and B, how they're related, if you put that, this also turns out to be the same. Okay, so when you add these two, you get half. Clear?
Yes, sir.
Yeah. Any other questions? So looks like we're out of time, so we'll discuss total independent reflection in the next class.
Excuse me, sir.
Yeah.
So with respect to the arbitrary wave, the way we have defined it, what fundamentally is A of k? Like when you take that at t equal to 0, we're saying that E and A are Fourier transform pairs. But then when you're defining in the beginning itself an arbitrary wave, then how exactly are we defining A of k? Is it got to do something with the amplitude of each of the waves?
So you can calculate A of k, right? So if you're given a wave packet E of z, right? If you know the wave packet in space E of z, if you know, then you can take the Fourier transform and calculate A of k, right? Or if you're doing the other way, let's say you're starting with plane waves and adding them up together, then you can add them up with different weights. Right? A of k are basically the weights with which you add. So the plane wave with k equal to k1 will have amplitude A of k1. K equal to k2 will have amplitude A of k2. Right? So depending on how you add these up, you'll get a wave in space according to that. Right? So practically, there are different ways of measuring it, right? So, you know, for example, when a beam sort of diffracts away, in the far field, what happens is that because of the diffraction, the spatial form, right? So, if you have E of z in the beginning, so let's say you have some pattern here, E of z, or let's take in the other coordinate. So, let's say you're propagating in the z direction, you have some E of x. Wave packet in the transverse direction, right? So as the beam goes away and diffracts in the far field, it will become something else, right? And that something else turns out to be A of k. So in this case, that will be A of kx. So if you take an x, that will be A of k of x, and it will be the Fourier transform of this. Okay, that just comes from the diffraction equations. So automatically, so that's one way to measure. In case, so let's say you start with a wave packet, I want to measure AK, you just let it diffract, and then in the far field you measure the envelope basically, and then that is basically right. So A of k are the different wave vectors present in my wave, right? With different waves.
Yes, sir.
Excuse me, sir.
So yeah, or in terms of the analogy of the signal, right? These are the different spatial frequencies, right? Adding up to give me my complete wave, right? So the spatial pattern that I get depends on how these different spatial frequencies are adding up. Similarly, like for a time domain signal, how the time domain signal looks depends on how I add up the different sinusoidal terms with what weights and phases I add them together, right? So basically the same concept.
Excuse me, sir.
Yeah.
Sir, you wrote for the plane wave, you said E naught is a complex number. So what does that signifies? I mean,
So for
can you
if you're just considering one wave, then it actually doesn't signify anything, right? So let's say if you're just considering one wave traveling through a medium or something, then that phase is irrelevant, right? So if I write this as some mod of E naught times e to the I theta, then this is just a global phase which is irrelevant. But now consider, let's say I have two different waves, right? I have two different plane waves coming into the medium. Then what is a physically relevant quantity is the phase difference between them, right? So you have two different waves. So each of them have their constant phase wave fronts. Right, so for example, you have this wave and it has these wave fronts, right, repeating after a wavelength, right, and now I have another wave. So now if I take the same phase wave fronts, if they line up exactly, right, then the phase difference between them are zero. But they could be shifted, right? So like there could be, this could happen relative to this could happen after some distance. Similarly, the next phase front here comes after some distance from here. So there's a phase difference between these two waves. Okay, so that's a physically relevant measurable quantity. For example, if you do interference, we can see, right? So in that case, so if you have E1, which will be some gap E1 e to the I something, then you have E2, right? Again, so this will be e to the I. Then this E1, E2 being complex matters, right? So for example, I could keep the same magnitude of E2 here, but add a phase, and that would be a different physical situation.
Okay, sir, got it.
But if you have just one wave, yeah, then it doesn't matter.
Okay, sir. Thank you.
But it's important to take that into, so for example, so next class we'll study reflection of interfaces and total internal reflection, etc. Right? So then we'll see that there is a phase shift on reflection, right? So how that's manifested is that if you take this as a complex number, this gets multiplied by another e to the I theta, right? So the reflected wave and the incident wave has a phase difference. Or for example, if you're doing interferometry, you take one beam, split it into two parts, and then recombine them, right? So the two parts can acquire a phase difference. So when you recombine them, that phase has to be taken into account.